Okay, great that you're all here at the second talk of the day. So that's quite something, I think. That's the first time. But we will see whether this will get into a thing. And I'm very happy that we have Irene here. And I found out by her work about a whole year ago, because I'm very much interested in the statistical physics systems where you have three values, the -1, 0, 1 case. And for me, reading all the physics literature is quite hard, but then I found out Irene's papers, and that helped actually a lot. The last 2 days he has been here to see how we can apply these models also in psychology. Her own application is more on opinion dynamics. And yeah, the floor is yours.
Thank you, Han, for the very nice introduction. It's a pleasure for me being here at the IS, sharing a bit of my research today with you. I am Irene, a PhD student at the University of Barcelona, Institute of Complex Systems, currently finishing it. And the topic of my research is opinion modeling from a statistical physics perspective. But at the end of the day, what we all, not working. It's frozen.
Yeah, click on your, maybe you can get the chair from upstairs.
Let me just restart it, maybe. I think. Oh, okay, here we go. Bit of spoiler, it doesn't matter. Okay, so at the end of the day, what we all sociophysicists try to answer is how the society can agree or reach a consensus on very important questions. Because let's face it, there's a bunch of important issues we should address as a society. Like this image is about global warming, pollution in the area of Wuhan after the lockdown. There are many, many questions in which we need to agree, and not only separated questions, but there are some comorbidities between some of the aspects we need to address, let's say in this context of the 2030 agenda. This is an image from the city of New York showing that the levels of pollution in the air are highly correlated with the neighborhoods with higher levels of poverty as well. So it's not a simple thing, it's very complex, let's say. And we are not very good at reaching agreements, right? So we are all well aware that in these international conventions like Kyoto or Paris, sometimes politicians just got there and say, what's the problem? There's no problem here. There's not climate change. It's just, it's nothing. So reaching consensus nowadays, it's not something easy, even if it's very important and critical for us to do it. So the thing is that, okay, what can we do as physicists to address this kind of problems or questions? Well, statistical physics is a discipline that studies particles that are very similar between them. So they have some common traits and that they interact. So there are some kind of forces, there are some kind of interactions that may them behave in certain ways and that may arise some kind of emergent properties. And these particles can be in different states. These particles can move around. And yeah, so from the physicist perspective, we individuals, we people are those particles. And we can be in different states. For instance, the people on the right has an empty plate. People on the left, a person on the left has a full plate. And they can obviously interact. So, yeah, let's say that it's kind of important for us to uncover the different patterns that arise from these different states in which people can be and the interactions that they may have and how can they eventually get to an agreement, get to a polarized situation. So there's a bunch of models in literature. We don't have still like a complete theory for sociophysics, but what we do have is a bunch of laws, let's say a bunch of models that try to specifically modelize particular situations in, that are more suitable for some contexts, less suitable for others. Some of you may be familiar with the Butter model that takes into account two possible opposite states, or the Potts model that takes into account several states, but they are not kind of related between them. There's not a notion of distance between the states. It's much like a categorical model. And when I was finishing my bachelor, and I went to my supervisor to discuss, which was going to be the topic of my bachelor's final thesis, we were facing in Catalonia, let's say, a political situation a little bit complicated. So at the time, people in Catalonia, which is a region of Spain, where I come from, some of the population, a part of them, wanted to become independent from Spain. And there were a lot of manifestations, a lot of classes canceled, a lot of people discussing. It was an everyday conversation, actually. It was a very hot topic. And at some point, oh, sorry, I skipped this image. So this is from Nature from 2023. You're seeing the evolution across the years of the sentiment of national Catalan identity of Catalan people. The different colors represent people with mother tongue being Catalan or being Spanish, also which kind of main media do they consume, if this regional or not. But the thing is that you can see here that around 2013, there was almost in all groups an increase of this sentiment of national Catalan identity. Nowadays, in 2023, is decreasing because things, didn't turn well for the independencies. So yeah, nowadays people don't care anymore. But at the time, it was a very hot topic. So at some point, politicians decided to make several referendums asking people what did they want. And in these referendums were not only two options. It was not non-independency or yes independency, but there were three options. So there was the pure no. I only want that people remains as a region of Spain, just the way it has been in the last years. But there was a complete yes. Yes, I want to become a totally independent country, so not related to Spain at all. And there was this intermediate option. It was that yes, but no. So yes, I want to become independent, but becoming a federal state in confederation with Spain. And it turned out that this third option was not kind of being undecided or don't care, don't know. No, it was an option that was sometimes the majority of the votes go to this third option. So we were thinking, okay, what if those three states model sometimes are just eyes and light models with beacons? What if we introduce some kind of driving force towards neutrality that comes from the interactions between people who want the neutral option, and they actually interact, they talk, and they can propagate this central opinion. Okay, so go ahead.
How neutral is in this case? No, I mean you put it in the middle, but it isn't really. It's still on the left side of the.
Yeah, right.
You're still voting for independence in some sense. So
yeah, I was discussing this with Lauren during lunch. Thank you for the question, actually. So this is the way that the paper vote was designed, but actually. Yeah, it was like in the middle, because even if you are not voting for complete independence, okay, becoming a federal state, it's quite a step for a region of Spain, right? And also, when you were there living the situation and talking to people, it didn't feel actually that people who wanted to become a federal state was more biased towards the no at all, quite the opposite. So in the end, we decided that maybe, it was kind of orthogonal. So people who wanted this federal state were people that didn't want either one or either the other one. It didn't feel really close to one of the two opposite states at all. They really wanted this as a third independent option. Okay. So yeah, does that answer your question? Thank you. All right, so now we have settled which are the states in which our particles, individuals, can be. So this is there are two opposite extremist states, and this is the neutral state. And since the position of neutrals, since the position of neutrals sometimes vary over time, so this amount of votes towards the central opinion, let's say, was not constant in time, we introduced this parameter alpha of the model, which actually what does is tune the degree of conviction of people holding the central state. All right, so we already have defined the states. Now we're going to define the interactions. Other people go to the bar, people go to the university, at that point where several conversations ongoing. And what we do, classically inspired by magnetic Ising-like models, is based on the principle of homophily. So when people engage in a conversation, they try to align their opinions, or at least it's less costly from an energetic point of view to be in an agreement than to be in disagreement. So we build this object that's called energy, which is a sum that runs over all possible pairs of people conversating. So if two extremists were conversating, this contributes to the energy with a reward, like lowering the energy, because these two extremists agree, so it lowers the energy. Okay. If two extremists but with opposite opinions are conversating, this has a large penalization, because it's like they are the most far apart opinions, so there's a large penalization. And what happens if two neutral or central people are conversating? There is a reward, because there is an agreement between the two of them, but this reward is tuned via the neutrality parameter. It's going to depend on which this alpha is larger or lower. The degree of conviction of neutrals is larger or lower. And finally, if an extremist and a neutral are conversating, they don't agree, so there is a penalization, but this penalization is a bit smaller. Actually, it's half of the penalization imposed to people with totally opposite states conversating. All right. So, yeah.
Why does it depend on the degree of conviction of the needle?
I'm sorry. Can you repeat again?
The penalty, the penalization.
Yeah. For the neutrals?
Yeah, it could depend on how convinced are the green.
Exactly. So there is a reward, not a penalization, because it is they are agreeing. They are agreeing, right? We are here. Or you're asking for?
No, I mean, I'm asking for the
last. Okay.
One, yeah.
No, it's a fixed penalization as well, because those two or three states are orthogonal. Let's say if I'm neutral, I don't want nothing to do with extremists. So it doesn't matter how convinced I am. There's just a penalization because we don't agree. That's it. So the reward comes toward interactions to pairs of people in neutral state only. Okay, so this is kind of, it's not propagating somehow. You know, there's no term here. We could have included, I guess, but I don't think that much have changed. Only maybe the tendency towards neutral consensus would have been faster, but in the end, the overall behavior of the system, I don't think that it changes much. Okay, so to move towards, okay, what we see here is the energy landscape for a system of fully connected agents for a complete network. Okay, for the simplest possible case, because this is like to model everything first in the most simple possible case, even if it's not very realistic. I don't know if you know about the spherical cow, if you're a physicist, but when we are modeling a cow, it's a sphere, yeah, more or less. Whatever, not very realistic, but at least mathematically treatable. So we can gain some insights from it. And you see here, of course, see if the connections are all-to-all, are completely symmetric, the macro state of the system comes determined only by the proportion of agents in each possible opinion state. So for instance, if we are here in this point, we have 30 agents in the neutral opinion, 50 agents in the +1 opinion, and 20 agents in the -1 opinion, okay? And the colors represent the energy. And the energy varies with the parameter alpha, okay? So, of course, see the attractors of the systems, the potential wells, are in the vertices of these triangles. So it will be consensus in the +1 state, this will be consensus -1, and that will be consensus neutral. And at some point, when the parameter alpha exceeds the value 1, the potential well corresponding to the neutral consensus becomes deeper than the potential well corresponding to the extremis. That is less than 1, then the extremis are the ground state of the system, the lowest energy. Okay. So this is for the fully connected network, as I told you. And this is the energy landscape. This other image here actually matches equally this other triangle here. It's actually the same. It just looks a little bit different because what I'm representing here is in the vertical axis, again, the number of neutrons, but in the horizontal axis, I represent what I call the magnetization. We call it magnetization also for historical reasons, which is the difference between extremis in the +1 opinion minus the extremis in the -1 opinion. So this way we reduce the variables of our system from 3 to 2. So it's more efficient. Okay, so what you see here is, for instance, if we start in a macro state here, the gray arrows points the average displacement, the most probable direction, let's say, our system is going to move to, because you're going downhill, okay? All systems tend to minimize their energy, so you're going downhill. So you see again that the attractors of the systems are the vertices. And one curious result is that no matter how small is the value of alpha, if it's positive, and we are in a situation in which we have extremis, but they are balanced, we have half of the extremis in one opposite opinion and the other half in the other opposite opinion. We're always, oh, sorry. So we're always going to end up in consensus into the neutral state. So this is a nice dynamical result of our model. Okay, but this is at 0 temperature. So this is if we only allow movements downhill. But what if we allow movements that allows us to jump these energetic barriers here, these red areas which represent the hills of our energy landscape? Well, we introduce a parameter that's called temperature. That's basically a coarse graining of all mechanisms that makes us not tend necessarily to homophily. That gives us enough energy to disagree. To don't care about what you're telling me. I can disagree with you. I'm okay with that. So, okay, we have two parameters for our system, alpha and temperature. And this is the phase diagram for the fully connected network. So in this case, what we see is that we have 4 possible outcomes. You can see here very, very quickly which they are. So first of all, first outcome is extremism. So right here, shows perfect. So extremism is this region of the phases diagram. And it corresponds to having all people in one of the 2 extremis states and no neutral people. The second outcome is consensus in neutrality. So we are in this region of the parameters. So we have alpha above 1, yeah, and low temperature. So in this case, we go to neutrality, so 100% of neutrals and no extremists. We can also have a mixture because this line, this green line here, correspond to what it's called a first order transition. So imagine this diagram is very similar to the diagram obtained, for instance, for the different phases of water. So in water, for instance, we can have ice or liquid or vapor, right? And here we can have extremism or we can have neutrality. So in this line here, what we will have is a mixture of extremists and neutrals. And since it's a first order transition, it's like when water boils, and water boils always at 100 Celsius degrees, right? So you see here the evolution of the parameters of magnetism and neutrality. You see these jumps that occurs at a fixed amount of temperature. This is because we are in the first order transition, always at the same temperature until we completely change the phase. And then if we keep heating, of course, temperature can keep increasing. And the last outcome, that's complete disorder. This is something that also occurs with liquids, but it's not so commonly observed in usual situations. But yeah, there's a transition. It's called the superfluid transition. That basically, when you are in this region of parameter low alpha, well, actually, it doesn't matter the value of alpha. When you increase the temperature enough, what you get is complete chaos. So you get 1/3 of the population in the neutrals and zero magnetization, but not because there are not extremes. There are extremes, but there were 1/3 and 1/3. So magnetization cancels 1/3 minus 1/3. You basically have everybody don't caring at all about what their peers are telling to them. So conversations don't matter. I'm only in my own state. I don't care about what other people is telling to me. Okay, so if you want to know more about the applications of this model to the fully connected topology or random topologies like Irene random networks, Barabasi-Albert networks, this is published in this preprint here in arXiv. That's currently in peer review. And we also applied the model to more realistic topologies. This is a paper published in Entropy in 2022. And it turns out that when you apply the model to more realistic topologies, that what have in common is that they have a very clear community structure. The absorbing states are not consensus anymore. The communities themselves reach consensus within them, but they don't necessarily agree with each other. So there appears this phenomenon of echo chambers of opinion bubbles that are represented in this correlation matrix, but these white squares here in the diagonal. All right. But now what I want to talk about is what happens if we combine this opinion model with an active matter model. What's active matter? Active matter are models that take into account that the particles can have some energy, can eat, for instance, and gain energy, and then can self-propel towards through a certain space. This is what's called a random walk, generally in the literature. And this is already published as well in Chaos last year in 2023, if you want to take a look at it. But I'm going to explain it to you in more detail now. So we are including now dynamic networks, so no static networks anymore. So now the networks can change over time. So okay, now we are going to work only at low temperatures, so no jumps across the line of energy are allowed. Well, we model our physical space as a square, for simplicity, with periodic boundary conditions. So if at any point there's an agent that's moving towards that direction, it's going to appear automatically the opposite side of the square. Going there, it's going to appear here. Okay. And what we do is firstly to scatter our agents randomly in our square. And we assign initially random opinions to every agent. Then we settle a certain radius. So we only connect agents that live close enough. So we're going to have conversation with people who are close enough in our physical space. We have eliminated as well all the periphery, but we have chosen a radio that allows us to have a giant connected component that percolates all the physical space from one side to the other. And we start the simulation at low temperature. This is for alpha equal to 0. We'll see later what happens when alpha is not equal to 0. And the movement rules for now, it's going to be what we call the elastic movement. So all agents take a fixed step with a fixed velocity and a fixed length, okay? They move towards a new place. Then they are asked the question, do you want to change your opinion? Do you want to flip your state or not? And depending on the neighborhood they encounter in this new place, they can take the decision to change or not. In this case, since the red agents is surrounded by blue agents, he'd say, yes, I'm going to change my state to blue. And then in the next step, it goes back to the original position. So this is why we call it elastic, because we are always going towards a random direction, coming back to home, going to another place, coming back to home. Okay. Yeah.
Flipping, is this fixed or is this probabilistic in the sense that if you have so many neighbors, you have a higher probability of flipping, or is it always if you have 3 neighbors that are blue, you will become blue and all?
Yeah, if it lowers the energy, and the energy, remember, it's compute over the pairs of people agreeing, then I'm going to change. And since I'm working at low temperature, I'm not allowing random flips. Let's say, I'm not allowing people to say, okay, I disagree and I don't care, because we're working at low temperatures.
The direction of the elastic movement, is it like uniformly chosen? It changes every time?
Yeah, it changes every time. It's totally random every time. Yeah. So I can go together today to the supermarket and the next day to another bar or whatever. Okay. So this is what we have. The question is, are we going to reach consensus or not? And if we do, how much time is going to take to reach that consensus? So what we see here, the yellow bars, is the consensus time needed to reach consensus, if it is reached or not. And in the horizontal axis, it's the velocity, so the length of the step I'm taking towards the new position. And the in plot here is showing, with the pink bars, the ratio of failure to achieve consensus. So there's a threshold here below which the system fails a lot to reach consensus. Sometimes it does, but many times it doesn't. Because this blue line here is representing the aggregated reachability. So the ability of an agent to reach every other agent in the network. And this value saturates at this threshold to 1, so it becomes 100% probability of reaching all agents. But below having this aggregated reachability equal to 1, we keep failing and failing. And why is that? Because we're moving too low. We're only going maybe to the bar below my flat and going up. We're just vibrating around our equilibrium position, and we're moving so little that it's almost like a static network, like the networks we saw in the static case with the opinion bubbles and so. But if we increase enough the velocity, we see here that there's a minimum in which the system actually reaches consensus, and it does it really fast, in as much as 12, 15 time steps at tops. Okay, and since we are working at zero neutrality, this consensus is an extremist opinion, okay, yeah. But if we keep increasing the velocity, we still reach consensus, but it can take a lot of time. It can take so time that maybe virtually we are not reaching consensus at all. Other events are happening and other things are happening, and Yeah, and in an ideal case, maybe we will reach it, but look at this. It's almost like 2,000 steps needed to achieve this consensus at high velocities. And why is that happening? Well, because at high velocities, let's say 0.4, 0.5, we are allowing agents to move so fast and so far in a single step, and then the next step in a random direction, that virtually what we have is, yes, a fully connected network, but with blinking edges that change randomly at every time step. So in the end, it's very chaotic, and we reach consensus, but in a very, very long time. And this is what we have.
A question.
Yeah.
So with the periodic boundaries, is it varied? Is it you go back to the home?
Yeah.
You pick a long home?
Mhm.
It's just one radius that you're going to reach, or is it a maximum distance to travel?
The thing is that we only have explored the velocities up to 0.5 to avoid this kind of, let's say, loop in which I come back home in a single step.
So that my
that's
question is the velocity normalized by the
By the length of the square, which is 1. Yeah. Yeah. Thank you.
Another question?
Yeah.
How, I mean, this will depend on the velocity, but that also depend on the density of people you have, right? So kind of those two parameters are coupled, I mean, they are not independent from each other.
They are not totally independent from each other, right? But we have performed simulation. This is for 100 agents. We have performed simulations up to 500 agents, and it really doesn't change much, because what we do is to adjust the radio of connections. So I don't know if you remember that we have settled a radio, and this radio is actually ensuring that you have enough sparse network, and you don't go to the fully connected case, because the fully connected case is already studied. It doesn't make sense.
So
yeah.
depends when you increase density,
Yeah, you can-
scaling.
You're scaling the connection radio, you will still have the same connectivity pattern. Yeah. Okay. So this is for the elastic movement. Very well. But what happens if we don't require people to go home after moving? What happens if we really perform the classic random walk, in which people keeps moving, choosing a random direction each time step? Are they going to reach consensus? Are they not going to reach consensus? And how much time are they going to need, if so? Okay, so here you see again the consensus time. Again, we are working with alpha equal to 0. Don't worry, I will show you what happens with different values of alpha in a very short while. And what we see here is that they reach consensus always, because eventually, even if the velocity is very, very small, eventually, if we wait enough time, they are going to meet everybody else. So eventually they're going to reach consensus, all right? But it's going to take a long, long time. So at low velocities, it can be like 10,000 time steps. And another thing that's very curious is that here where we had this minimum, this very efficient velocity in which we reached consensus like in the blink of an eye, here we have a peak, we have a maximum. And we were thinking, why are we observing this maximum? And it turned out that it's related to the probability of switching my first neighbors and my second neighbors. So if I have a connectivity pattern in which I have first neighbors, say friends, and then they have friends of a friends, when the probability of that in this time step, I have a friend, and then the next time step, this friend is a friend of a friend instead of my direct friend, it reaches a peak. This is the maximum of, let's say, the consensus time, the amount of time steps that I need to reach consensus in this situation. And you'll see here what's happening. So this video matches this plot here. So you see that at some point, there is kind of a consensus in the red opinion, okay? And it seems kind of stable, but you'll see that when we reach 700 steps, it's going to go down again. It's going to happen about a few seconds. And Yeah, there you go. It's starting again to being a fair presence of blue agents in the simulation, and it's keep this bouncing between extremis opinion keeps becoming like a lot. It's so long, like it extends over long periods of time. So that's why it's so difficult for this situation to reach actually the consensus. All right, I promised you that I was going to show you what happened for other values of alpha. Here we have the phase diagram. In this case, in the horizontal axis, we have alpha, but in the vertical axis, we don't have temperature, we have velocity because we're working at low temperatures all the time. And the first thing we see here is this white line that indicates transition from consensus in extremist opinion and consensus in the neutral opinion. It's nice to see that it occurs a bit before the value of alpha is equal to 1. So when the consensus well in neutrality is a bit shallower than the consensus well in extremist opinion. So there's kind of a bias towards neutrality. And when you increase velocity, this bias is even shifting towards lower and lower values of the parameter alpha. Up to a point, which is this 0.8 value of the parameter alpha that's kind of related with those transitions for the fully connected network that I was mentioning before. This is when the first order transition from order to disorder and the second order transition from order to disorder and the first order transition, let's say from extremism to neutrality, meet at that very value of alpha. And this is kind of the threshold in which it doesn't matter how fast you move, neutrality is not going to be an option anymore. Okay, so now we're going to change the movement rules a little bit. Now we're going to consider that in some occasions, agents may, in a conscious way, not just randomly, not just keep moving no matter what, but when they may encounter like-minded individuals, maybe they are happy there and they want to stay, and the other way around. So now we are keeping fixed the velocity for the neutrals. So let's consider that neutrals, well, since they are not extremists, they don't care so much, and they are going to keep moving at a fixed constant velocity. But for extremists, it's going to be a bit different. So imagine that an extremist red agent comes to this neighborhood and it says, okay, I have a majority of friends that are like-minded. I like it. I'm going to stop. I'm not going to move anymore. And the opposite thing also happens if we have a red agent that comes here, surrounded by blue agents. Say, I don't want to be here. I'm going to keep moving. And I'm even going to double the velocity. So I'm going to move as fast as possible to find another neighborhood in which I'm more comfortable. Okay. So this is the scheme of movement now.
And
yeah.
What's the threshold for continuing or halting? Is that just the majority?
Yes, it's just the majority. Majority of
In your
surround, yeah, the people you are connected with, and you're ignoring neutrals here.
Sorry?
You're ignoring neutrals, so neutral doesn't count. You're only counting extremists.
Okay.
So if you're with neutrals, it's okay. There's some neutral person here. All right.
The neutrals are also moving.
At the same velocity.
And how do they hold?
They don't.
Oh, they don't.
No, only extremists have different rules here. Okay. And now here are the phase diagrams for both the absolute value of the magnetization down here and the number of neutrals up here. And we observe something that physicists like a lot, which is non-monotonical behavior. Whenever there is a non-monotonical behavior, we're very happy because it means that something is happening with the interaction of the parameters we're exploring. So for instance, if we see here at velocity 0.1, along the alpha axis, along the neutrality axis, Well, when the alpha value is below 1, is low enough, we have magnetization very low. And if we see what happens with the number of neutrals, we see that it's 0. So this low magnetization means not that we are in a neutral consensus state or anything, but that we have an equal amount of extremists in each position, in its opinion. Okay. And then we keep increasing the value of the parameter alpha, and we will expect more tendency towards neutrality. Even if we surpass the value of alpha equal to 1, even if we are in a position in which the potential well of neutrality is deeper than the potential well of extremity, what happens here is that we increase magnetization. Instead of lowering magnetization and increasing the number of neutrals, what we are doing is like fostering that extremists agree in extremist position. So fostering extremist consensus by increasing alpha, by increasing neutrality. And then, of course, if we keep increasing and increasing indefinitely alpha, in the end, we reach some neutral consensus and we lower the magnetization. This has happened for low velocities. Then if we increase the velocity, we observe unexpected behavior, which is that this peak shifts to the left. So the number of neutrals and neutrality appears around 1, which is what we expected and what we obtained with the constant velocity model. Yes.
Are these results based on many repeated simulations with the same parameter set with different initial conditions?
Yes.
Okay, so the non-monotonous behavior is not due to the initial, is not related to the initial.
No, it's average over 100 different simulations. Yeah.
Yes, sorry, I don't understand what's happening. Why is it that when you increase alpha, so alpha is the how confident are the green one, right? The middle, the neutral.
Exactly. How the degree of conviction of the neutrals? Yes.
So what you change here compared to what you had in the first initial cases, and now people are moving, and then the non-neutral can hide.
Yes.
And
Or double their velocity.
Or double their velocity.
Yeah, if they are in a neighborhood with a majority of neighbors in the opposite opinion, opposite extremist opinion, they double their velocity.
Okay.
Can I ask one clarification?
Yeah.
So is velocity fixed? So it's like you reach a particular circle around your home location?
You never reach a circle. It's limited to 0.5.
Okay, so it's any value between, so it's there, okay.
So I still don't understand why alpha has an impact on the fact that on what's going to be doing the others, because from what I understood, the non-neutral one, they don't care about the neutral one in this situation.
Yes.
The heights not. So why is it that alpha has an impact here?
Okay, that's a very good question. So the thing is that somehow by changing the energy landscape, you change the path, the preferred path for the agents to move toward one attractor of the system or the other. And it turns out that by lowering this alpha so much, you favor that extremists can move from one opposite state toward the others. Somehow you have to think about it as hills and valleys, and somehow you are changing those hills and valleys in a way that you make them easier to transition. So sometimes what happens is that one extremist encounter one neutral that's moving around there, and then it's easy for the extremist to convince the neutral, and then the neutral become extremist, and then it's easier to go to a more extremist situation. Does that answer your question, more or less?
More or less, yeah, but I have to think about it.
Okay. All right, so here what I want to show is 4 examples of 4 different points in these phase diagrams. So here we are in high velocities over here and over here. for values of alpha that are below 1. So we are in this region and this region here. And we are observing now the distribution of consensus time, or not consensus time. Let's say the time until they reach a stationary state that can or cannot be consensus. So in this case, the consensus is always local. So it's not global. We are in the situation with the opinion bubbles, okay? Always. It is represented by these green bars here. And yeah, it's always like this. When we are in the region here, we have local extremist opinion bubbles because we don't have neutrals, but we do have extremists, and yeah. Okay, and we increase the value of the neutrality, but we keep the velocity high. We have more variety of outcomes. So we can see here that we can reach global neutral consensus, and that whenever this occurs, it occurs really fast, in less than 5-10 time step stops. But if it does not occur and the simulation keeps going, so if neutrals are not fast enough to convince everybody else to neutrality, then what we can have is both either polarized extremist consensus represented by the blue bars, or again a local consensus that in this case are opinion bubbles, but with neutral clusters as well, not only extremists like in this case.
When you say local opinion bubbles,
Yes,
so that's in this dark blue area there.
it's the green one.
Yeah, but it's
It's right
low
here.
alpha and it's
We are in this plot. We're moving here.
yeah, I understand. But so what's the ratio between the positive and the negative, or the right and left in these bubbles? I mean, is there
So we are
is
here.
that changing?
Yeah, it is changing, and it's pretty low. So the ratio is more or less we have the same amount.
Okay.
Otherwise, we will have high magnetization, and we have a pretty low magnetization in this case.
Okay.
Yeah. So, okay, we examined what happened for high velocities. Now we are going to the two cases of low velocities with different parameters, with different values for the parameter alpha.
But I have a question. You
Yeah.
can have low magnetization, still clustering, right?
You can have low magnetization, but still clustering. Yes, of course. This is what's happening right here. So here we have some green bars denoting local consensus, so clustering. But magnetization is low.
Yeah.
Okay, because the value of alpha is large enough.
Yeah.
So we have half of the, well, we have some opinion bubbles in neutral, some others in one opposite extremist state and the other in the other, and it's kind of balanced, so magnetization is low. Yeah. All right. Okay, so let's go to any other question? No. Okay. So let's go to the low velocities now. So first of all, velocity equals 0.1 and low value of alpha below 1 as well. So we're in this region here and this region here. So we don't have neutrons. And again, we obtain much more the same that we have obtained up here. Okay, so local consensus as well. And local consensus only with extreme opinion bubbles. And if we increase the value of the parameter alpha, we get to this situation here, in which again we observe several outcomes, but the number of neutral consensus now, the frequency of neutral consensus now, it's much lower than the number of neutral consensus up here. And pay attention that the value of the neutrality parameter is exactly the same. So this is not due to the value of the neutrality parameter. This is due to the velocity. Okay. Again, whenever it occurs very fast. And if for whatever reason the neutrals are not able to convince the others towards the global neutral consensus, we already have the possibility of having either polarized extremist consensus, or again opinion bubbles, so clusterized situation in which we don't have global consensus at all. So here are a couple of visualizations so you can understand maybe a little bit more what's happening, which is the dynamics of it. So yeah, this video here matches. Okay, so this video up here is for high values of the alpha parameter. So we are here, we're in this two plots, representing these two plots. I'm not representing these two because they are very similar and more boring, right? But these two here with more variety of outcomes are more nice. So the first video corresponds to a low velocity. So we are here. I should have switched the plots here. We're at low velocities here, and what's happening? It's that yeah, we're getting to clustered consensus. Okay, so you see that some extremist communities start forming. There are still some neutrals moving around, but at some point, as we were discussing when you asked me, these communities become large enough and they kind of trap the neutrals, they convince them, they trap them, and they become extremists as well. So the outcome is local polarized consensus. And in this other situation here, with high velocity, so we are here, we do reach neutral consensus, and we do it in only 4 time steps. So only 4 opinion updates for each agent, and we already have everybody convinced of neutrality thanks only to the velocity. The neutrality parameter is exactly the same for 4 videos. And well, yeah.
The lower left one was actually,
Yeah.
started out with a t = 0.
So
It had
a moment. Yeah, I'm sorry.
So,
I don't
so
remember.
yeah, so here you saw actually that, I mean, it seemed like that at t = 0, the greens were dominating in the initial condition. So I was wondering, how do you vary the initial condition? Do you have also different ratios of the 3 different opinions and different positions of individuals, or do you only vary the positions?
It's all at random. Always
It's all
all
at
at random. Yeah. But since we perform many simulations,
But
yeah,
but the probability of the initial opinion is then 1/3.
correct.
On average, but not every instance.
Not every instance.
But on average.
But, well, no, it's just a random draw for every individual.
Yeah, but then it's on average, it's a
Yeah.
third, but not for every instance. So it could be that one of them is 2/6. One initial condition is very rare. It could happen.
Yeah,
Yeah, but you have 100 you have 100 individuals, so it's like
and we performed as well for 500 individuals. I'm not showing here the results because a little bit more messy to visualize, but it doesn't change. If you 500.
Did you check if somehow your final outcome is dependent on your initial condition? Because it's, for example, in the Barton model, the outcome depends on what is a fraction of. So maybe, when you have like a final outcome that is a local outcome or a global the global neutral might depend on what is the fraction of individual.
But the thing is
At that specific initial condition.
but the fraction is always so close to 1/3, 1/3, 1/3.
At each realization.
At each realization,
okay.
very, very close, so close that the fluctuation
So it's
doesn't
not
matter.
that it's on average, it's.
It's defined at random. So randomly, you have that probability. If you toss, like, if you throw a dice 100 times, you're really close to.
Yeah, but you can, over 100 times, you can be very close, but then it depends how narrow is your distribution of the 1/2, right? It could be, for example, if you take 1/2, and you could have in some of the cases that you have much lower than 1/2, and some other cases you have much higher than 1/2, and then on average you have 1/2.
It can happen, but it's very rare. And if you increase the number of agents, it's even more rare, and we obtain the same results for 500 agents. So.
But what
Sorry, so what I'm saying is that I understand that you do an ensemble average, but what I'm asking is that, did you do your ensemble average such that you have a kind of a broader distribution around the, not
Oh, no.
have one third,
No,
one third,
no,
or
we haven't.
you're really close to one third at every.
Yes, every time for this model, for the fully connected network that I showed you at the beginning of the talk, yes, we actually perform for every possible combination of agents, which were the basis of attraction. Yeah, we did, but not for the mobile case agents. But mobile case, it's always starting from random initial conditions, so really close to one third, one third, one third. So the fluctuations are.
Which means that you are very close to a symmetric situation at the start.
Yes.
And so, you have any idea how these results are influenced if you're further away from that symmetric situation?
So
So
yeah, if you
just to-
obviously if you start with a majority of, let's say, blue agents, that is going to move like towards the consensus, toward the blue opinion. It's going to favor that. And if you start with a majority of neutrals, that's going to favor neutrality. So yes, this is something that we expect from the initial.
But if you have two extremes, so non-neutral, you just don't get consensus. Or do you still count as consensus within that group?
You can still get consensus depending on the value of the parameters. You can still get consensus, yeah, in one of the two extremes opinion. If you don't have any neutral, you won't have neutrality. But because nobody can convince you, no. So here, all is about interactions. All is about interaction in pairs. So a single agent, as isolated, let's say, it's not going to,
Well, then the consensus is immediate, I guess, because it's the only person in the system. But I'm thinking of like in two extreme groups, you never get consensus, right? They can't convince each other.
They can convince each other.
Okay, then I missed the point.
Yeah. Eventually, they can convince each other.
Yeah.
If they move. Let's say, for instance, you have two groups, one blue and one red. Yeah, and then one blue agent moves towards the neighborhood in which he is surrounded by reds. Then he changes, and then another one does the same, and it changes as well. And if it happens sufficient amount of times, you're going to get consensus in extremist opinion. That makes sense?
Yeah, but I'm thinking in the concept of halting, you would assume that there's these big blobs forming immediately.
Oh, in the halting, yeah, of course. If you start with two separated communities, everybody's going to stop and the movement is going to occur. Yeah, in the halting, yeah. Now I was thinking in the completely random movement without halting. So, sorry. Yeah. Okay. Very well. So, yeah. Just to summarize. I would like to say that I think that there's a lot of potential in the study of the interplay of different relevant parameters that we can isolate from human behavior. We can have some evidence from sociology or psychology that are really driving human behavior, and how they interact and how they interplay can drive us to non-trivial results and non-intuitive results, and it's really worth it to understand how that interplay is going. And then, as we have seen, that the reconnection patterns plays a major role in which kind of situation we're going to achieve, if it's consensus, if it's not consensus, and that in particular, a high ratio of reconnection patterns favors neutrality somehow. So if we move fast, if we reconnect fast, it's more easy for the agents to get to a neutral situation. And in the end, just to say that I went through a literature review when I started this project, and I didn't see many models, opinion models, mixed with these active matter models. And I think that since humans do self-propel, it could be very interesting to explore more combinations of these opinion models plus active matter models, and not only on physical spaces, but maybe on other kind of spaces, like virtual spaces, ideological spaces. So yeah, that's it. Thank you very much for your attention.